All right, let's talk about the sun. I mean, we see it every single day, right? But have you ever stopped to think about what's really going on inside that fiery ball? It's a place of just unimaginable violence and power. So today, we're going on a journey from its super pressurized core all the way out to its million-degree crown. Let's dive in.
Okay, so before we plunge right in, let's get our bearings. We've got to appreciate the sheer scale of what we're talking about here. It's so easy to just take our star for granted, but trust me, its stats are absolutely mind-boggling. First off, just think about the distance. We're talking nearly 150 million kilometers away. That's just staggering. And it's the reason why the sun, which is actually over 100 times wider than our entire planet, looks like just a small disk up in our sky. So, what's this colossal thing even made of?
You know, the sun's recipe is actually surprisingly simple. It's pretty much all hydrogen and helium, which are, the two lightest elements in the universe. Everything else, all the carbon, the oxygen, the iron, that stuff makes up less than 2% of the whole thing. But this simple fuel is what powers an engine of just immense, immense complexity.
And that engine, well, it has a really distinct structure. You can see it here in this cross-section. These are the layers we're about to explore. We're going to start right at the very center, deep in the core. Then we'll journey out through what's called the radiative and convective zones, past the surface we can actually see, and finally into that ghostly outer layer, the corona.
Okay, we are now diving deep into the solar core. And let me tell you, the conditions here are insane. The pressure is over 200 trillion times the pressure of Earth's atmosphere. The temperature? A cool 15 million degrees Celsius. Yeah, this is an environment where the very laws of matter they get rewritten. So what's happening in there? Well, at the heart of it all is nuclear fusion. This is the sun's engine. For something like 4.6 billion years, it's just been smashing lighter elements together to make heavier ones. And in that process, it converts a tiny, tiny fraction of mass into a colossal amount of energy. Yep, that's Einstein's famous E equals mc squared in action.
So, how exactly does that work? It's a process called the proton-proton chain. Basically, in all that crazy heat and pressure in the core, hydrogen nuclei, which are just protons, get slammed together. It's a three-step dance, but the bottom line is this. 4 hydrogen nuclei go in, and 1 helium nucleus comes out. Now, the helium nucleus is just a tiny bit lighter than the 4 hydrogens were, and that little bit of missing mass, boom, that's what's converted into pure energy.
Okay, but here's the fact that's absolutely going to bend your brain. That energy, those photons of light, they don't just shoot straight out of the core. Nope. The sun's interior is so incredibly dense that a photon has to take what's called a random walk. It's constantly bouncing off atoms, getting absorbed and re-emitted, just zigzagging its way out. A journey that would take light just a few seconds in empty space can take hundreds of thousands of years inside the sun. Isn't that wild? So, after that incredibly long journey, all that energy finally makes it to the sun's outer layers, and this is where it creates the seething, visible surface that we can actually see, which is known as the photosphere. Now, to get to that surface, the energy has to travel through 2 totally different zones. First, there's that deep interior we talked about, the radiative zone, where energy travels by photons bouncing around. But the outer third of the sun is the convective zone. Here, the gas is a bit cooler and denser, so it actually traps heat. The only way for the energy to get out is for the hot gas itself to move. You get these huge rolling currents of hot gas rising and cool gas sinking. I mean, it's exactly like a pot of boiling water. And what you're seeing here, these are the very tops of those convection cells. This pattern is called granulation. The bright centers, that's the hot plasma bubbling up from below. And those dark lanes surrounding them, that's the cooler plasma sinking back down. You are, quite literally, watching the surface of the sun boil. And just to give you an idea of the insane scale we're talking about, each one of those individual granules, those little bubbles of boiling gas, is about the size of Texas. Let that sink in. The sun's surface is basically a seething carpet of continent-sized storms. Wow. All right, so now we're going to move outward, leaving that dense interior behind us and heading into the sun's atmosphere. It's incredibly thin, but it's also unbelievably huge. And this is where things start to get really weird. I mean, think about it. You'd expect things to get cooler the farther you get from a giant furnace, right? But the sun, it completely defies that logic. The visible surface we were just looking at is about 6,000 degrees Celsius. But once you get out into the corona, the outer atmosphere, the temperature skyrockets to over 1,000,000 degrees. How is that possible? Well, that's one of the biggest unsolved mysteries in all of astrophysics. So, really, how can the atmosphere be so much hotter than the surface? The answer, it seems, lies in a force we haven't really talked about yet, a force that goes from being kind of a background player deep inside the sun to taking center stage out here. And that force is the magnetic field. Turns out this magnetic field is the hidden engine that drives almost everything we see happening on the sun. We're talking everything from those dark spots on its surface to the mystery of that superheated atmosphere. It is the key to understanding the sun's dynamic and, yeah, sometimes really violent personality. The most obvious signs of this magnetic field? Sunspots. You've probably seen pictures of them. They look dark, but it's only because they're cooler than everything around them. And why are they cooler? Because you've got an incredibly intense magnetic field poking right through the surface, acting like a cap and stopping that hot boiling gas from bubbling up from below.
And what's really cool is that these sunspots reveal a beautiful long-term pattern. When scientists plot where they appear over many, many years, they migrate from the middle latitudes down toward the equator, and it happens over a repeating 11-year cycle. It creates this amazing butterfly shape you can see here. It's like the sun has a heartbeat.
So, of course, that begs the question, what's going on deep inside the sun that's driving this powerful and really predictable magnetic cycle? Well, the answer is something called the solar dynamo. See, because the sun is a giant ball of gas, not a solid rock, it spins faster at its equator than it does at its poles. This is huge. This difference in rotation speed grabs the sun's magnetic field lines and stretches and twists them, just like winding up a bunch of rubber bands. And here's what happens. Over time, these tightly wound up magnetic ropes get so twisted, they become unstable, and they burst right through the surface. And where they loop out and then back in again, that's where we see a pair of sunspots. It's a direct connection between what's happening deep in the interior and the activity we see on the surface. So cool. And the ultimate and I think most beautiful expression of all this magnetic power is the corona itself. You can only really see it during a total solar eclipse, when the moon blocks out the sun's bright face. And then, wow, you can see how all that plasma is trapped in these magnificent loops and streamers, perfectly tracing the magnetic field lines as they reach out millions of kilometers into space. So, from the nuclear fusion hammering away in its core to the magnetic chaos of its atmosphere, the sun is just this incredible place of constant creation and change. And this magnetic engine doesn't just put on a beautiful light show for us, it also drives the solar wind, this stream of particles that constantly flows out and slams into our own planet's magnetic field, creating what we call space weather. It all just makes you wonder, what other amazing secrets is our star still hiding, right there in plain sight?